In the previous videos, we took a look at solving for the pH or the Ka of a weak acid. For this one, we're kind of flipping things a little bit around, and instead of asking anything about acid, I'm asking you to solve for the pH of a base. And so for this particular problem, I'm using my B here to represent any of your weak bases. Remember, I'm not talking about strong bases because strong bases will completely dissociate, same way that strong acids will. We talk about weak bases are typically going to exist in equilibrium with their products. And so for this particular situation, I'm asking for you to determine the pH of a solution of 0.34 molarity base with a Kb of or equal to 5.00 times 10 to the negative 5. And so very similar concept here. But instead of looking at acids like we did with the previous problems, we're looking at base. But the steps are still basically the same. If we know a concentration of just our base, we have to use a Rice table to figure out the concentrations of all our other stuff. Then if we know some type of relationship between our concentrations and our Kb, we can set up another equation, plug and chug, solve for x, figure out what you got to do in order to kind of get to the final result. And so, setting up our Rice table, one thing you should notice that this is completely different arrangement than it was for acids. Remember, with acids, you add an acid plus H2O, and you end up creating your hydronium ions and the conjugate base to that acid. In this case, we're looking at a base. And so a base plus water will give you a Hb plus OH minus. That Hb plus is the conjugate acid of the base you're given in the problem. Your hydroxide ions are just what happens whenever you dissolve a base in water. And so in this case, you're ripping a hydrogen off from the water to produce the OH minus and slapping it onto the base to give that Hb a positive charge. Very similar to the acid, if we know something about Kb, we know Kb is going to be equal to the concentrations of your products divided by the concentrations of your reactants. So here our concentrations of our products are going to be the Hb and times the OH minus. And so water, again, is still involved in the reaction, but we're going to consider it a pure liquid, so therefore the concentration is not going to change. So it's not going to have any initial change equilibrium values. In addition to that, because it doesn't change, we're leaving it out of the equilibrium constant equation. And so your reactants are just going to be just the concentration of your base. So now that we know this bit of information, let's start plugging in what the problem gives us. Fortunately, it's not too much, but it's enough for us to get by. And so we know our initial concentration of the base is going to be our 0.34 molarity because that's what's given to us. We know the initial concentration of our Hb plus and our OH minus is going to be 0 because initially these things don't exist. So if we kind of plug in those values, we now have initial concentration of our base is 0.34. The initial concentration of our Hb plus and our OH minus is going to be 0. So the change occurs very similar to in the acids. Whatever amount of B decomposes is going to create a mole of Hb plus and a mole of OH minus. Because this is a 1-to-1-to-1 relationship, we know for every 1 mole of B that disappears, 1 mole of Hb plus and 1 mole of OH minus is going to form. And so we can represent this by minus 1x for your B and plus 1x and plus 1x for your Hb plus and your OH minus. And so at equilibrium, your base is going to be equal to your 0.34 minus x, and your equilibrium concentrations of your Hb plus and your OH minus are both going to be x. And so using our equation for our Kb, we know our Kb, we now have some type of form of our concentrations of our OH minus, our Hb plus, and our and our B, so we can plug those in. So one thing I have to point out, please understand, as I kind of mentioned with the acids, this is a weak base. So therefore, this minus x is going to be very, very, very tiny when it's compared to this 0.34. And so I'm making the assumption that because our Kb value is times 10 to the negative 5, that this number is going to be relatively tiny compared to the 0.34. So I'm dropping out this whole factor of, or the portion of minus x. And so here we're going to be looking at HB plus is x, OH minus is x. Our B is going to just be the 0.34 drop off the minus x. So making lives a little bit easier. Assumption is going to be safe. I promise you're going to be okay. But whenever you kind of go through and solve for this, I end up with an x equals 4.12 times 10 to the negative 3 equals, again, the x there and the x there and not that x, but these two x's. We are going to be looking at the concentration of our hydroxide. And so, great thing for us, the same fancy equation that we can use for pH also works for pOH. And so our pOH is going to be equal to the negative log of our hydroxide ions. So here our pOH is going to be equal to the negative log of our 4.12 times 10 to the negative 3 that we saw for using this portion right there. And so our pOH comes out to 2.4. And so if we are looking for the pH, we know a relationship between the pH and the pOH. And so the pH is going to be equal to 14, which again is that pKw minus the pOH. So here we know our pOH, we know the pKw is going to be 14, so our pH is equal to 14 minus 2.4 equals 11.96. One thing I have to point out, this is just one way of solving this problem. There are a couple different routes you can go. None of them are incorrect as long as you end up with the correct answer.